Hello everyone, welcome to this video series called Embedded Essentials, Making the Right Choices. Whether it is a processor or OS or connectivity technology, as an embedded engineer, one has to choose the right component from seemingly infinite choices. In each of the video, we will take one aspect of the design, discuss the choices, and I'll outline a framework we follow at Embien. I hope this will be helpful to you in your design process. In this first video, we will discuss about processor selection, how to choose among the different choices, microcontrollers, microprocessors, different architectures, dozens of vendors and thousands of specific parts, and so on. How on earth do you choose the right one for your project? Feeling overwhelmed? You are not alone. I am Saravana Pandian, CEO of Embien Technologies, and I have been navigating this complex landscape for over 23 years. From simple 8-bit to 16-bit systems to powerful multi-core MPUs running complex AI algorithms at the edge, the challenge of process selection is a tough one. Over the years at Embien, we have developed a framework that helps us cut through the noise and make informed decisions. In this video, I will share that framework with you. Choosing the right processor isn't just a technical decision. It impacts cost, development time, power consumption, and ultimately the success of the entire product. Let's acknowledge the reality. The sheer volume of choices is staggering. We have microcontrollers, small, integrated, often cost-optimized devices that are great for dedicated tasks. Cortex-M series, various 8-bit and 16-bit families fit in this category. Microprocessors, or MPUs, more powerful ones often requiring external RAM and flash, typically running operating systems like Linux and Android. Cortex-A series, x86, high-end RISC-V cores are some examples. Different architectures. While primarily ARM dominates the market, RISC-V share is rapidly growing. There are some legacy and specialized architectures as well. Countless vendors, NXP, Renesas, ST Microelectronics, Texas Instruments, Microchip, Infineon, Nvidia, Qualcomm, and many more, each with their vast portfolios. Specific variants. Within one family, there can be hundreds of parts, differing by clock speed, memory size, peripheral mix, temperature grade, packaging, and security features. This is a crucial problem. A wrong choice can lead to performance bottlenecks, excessive cost, or even require a complete hardware redesign down the line. So, where do you start? Before you start using the framework, the first thing is to capture the system requirement. What exactly does the product do? Is it a simple sensor node sending data periodically? An IoT gateway collating data and pushing to cloud? A complex HMI with a graphical interface? A security camera during AI inference? List every functionality, every interface needed, every aspect of the product. This is your foundation. Let us now go into the 9-step processor selection framework. Like a funnel, we start broad, and with each step, we narrow down the options until the right choices become clear. Step 1. Performance needs. How much processing power do you really need? Are there intensive computations like DSP or AI inference that might need dedicated hardware accelerators? What is the required clock speed? This often helps distinguish between typically low performance real-time focused MCUs and higher performance general purpose compute MPUs. Step 2. Memory and storage. How much RAM is required for your operating system, applications, and data? How much non-volatile storage is needed for the code and file systems? Are we going to run RTOS or Linux? Is it going to be a headless device or having a display? Based on these questions, decision can be taken between MPUs and MCUs. Step 3. Peripherals and connectivity. List all the interfaces the device needs: USB, Ethernet, Wi-Fi, Bluetooth, CAN, I2C, SPA, UART, ADCs, DACs, GPIOs, camera interfaces, and so on. How many of each? What speed or resolution is needed? This is a major filter, as different processors have vastly different peripherals. Don't forget the quantity and specific features. For example, rather than mentioning as Ethernet interface, go for 2 gigabit Ethernet interfaces. Step 4. Power constraints. Is the device battery operated or line powered? What are the maximum power consumption limits? What about the low power modes and backup sources? MCUs often excel in low-power applications with sophisticated sleep modes, while MPUs typically consume more power but can be optimized to a good level. Step 5. Cost and availability. What is the target unit cost in the expected volume? The unit price of the processor itself is critical, but consider the cost of the external components it requires like power management ICs, clocking circuitry and so on. Is the part readily available from multiple distributors? What are the lead times? Step 6. Development ecosystem. This is very important. What development tools are available? Is there a stable, free or affordable IDE and compiler? How about the OS, middleware, libraries and drivers for peripherals? Is there an active developer community and good documentation? A powerful chip with poor tools can be a recipe for a disaster. Step 7. Physical constraints. What are the size limitations for the PCB? This dictates the required package size like QFN, VGA and pin count. What is the required operating system range? What is the required operating temperature range? Any specific qualification either industrial or automotive? Step 8. Security needs. Does your device handle sensitive data? Does it need secure boot, hardware encryption, decryption, or physical tamper protection? Step 9. Future-proofing and scalability. Do you anticipate needing more performance or features in the future product revisions? Or they are compatible, higher performance part in the same family that you can easily migrate to with minimal software changes? Consider pin compatibility and software reusability. Following these steps will significantly narrow down your options and help you choose the right part. Here are the few additional insights. Don't over-engineer. It is tempting to pick a powerful chip just in case, but this adds cost, complexity, and power consumption one might not need. Start with the actual requirement and add headroom strategically. Evaluate the total cost of ownership. Factor in not just the chip price, but the cost of development tools, potential OS licensing, and the time your engineers will spend on learning that platform. Talk to the vendor. For serious projects, engage directly with the vendor FAEs. They provide crucial insights, roadmaps, and support. Prototype key risky areas. If a peripheral or a performance level is crucial and potentially difficult, get a low-cost development kit for the candidate chip and test that specific aspect yearly. Supply chain reality check. The last few years has taught us the availability is as important as price. Check lead times and consider if pin-compatible alternatives exist. Leverage your team's expertise. If your team has deep expertise with a particular architecture or vendor, that can significantly reduce development time and risk. Don't underestimate the value of familiarity. So, while the embedded processor choices are enormous, by applying our processor selection framework based on the application's true requirement, performance, memory, peripherals, power, cost, ecosystem, physical constraints, security, and future needs, one can systematically filter down the candidates to the truly suitable one. It is a process that requires careful analysis, but with experience, it becomes much more intuitive. The goal isn't just to pick a chip, but the right chip that sets your product up for success. I hope this 9-step processor selection framework is helpful for your next embedded project. If you find value in this video, please give it a thumbs up and subscribe to the channel for more insights from our team at Embien Technologies. In the description, we have shared a link where you can share your requirement and our team will help you with the processor selection process free of cost. Thanks for watching and I'll see you in the next video.